now is the last thing of the day, our closing keynote. We're really, really delighted to have Aslam Khan, who's going to be talking to us about property-based thinking. Aslam, it's you. Or thinking in properties. Sorry, bye.
Hi, everyone. I couldn't see the name of that insurance company. Was that Marshmallow? Okay, I'm from South Africa. We have an insurance company called Pineapple. And I think more and more, and another one called Naked. So insurance companies is one of the most boring industries or domains you can ever come across, but we have to live with it, and it's like a grudge purchase. But anyway, so I'm from South Africa. It's good to be here. It's the first time I've been here. Between yesterday afternoon arriving and today, when I've walked through the streets of Budapest, I've just noticed lots of smells of food. And I'm looking forward to enjoying some of that. So, thinking in properties, it's a direct reference to property-based testing. Anyone here has done anything with property-based testing? Please show your hands. All right. Anyone who's heard of it but not tried it? Okay. So, it's one of those things that I was attracted to when I first started dabbling a little bit with Haskell, because one of my good friends was incredibly proficient with Haskell, and I never got it. I never got what the hell this quick check thing was about. And over a period of time, I've went towards it and I've walked away from it. But I'd say in the last 2 years or so, I've given it a solid shot to see what's behind this, and was quite surprised by what I learned about myself and the way I approach solving problems. And today's talk is mostly about that. You'll see some code. It's going to be incredibly simple code. Most of it is in Python or Python-like. But it's not about the code. It's about how it helped me change the way I think and how I work with certain problems. So it's about that. You're going to see reference to at least one or only one property-based framework called Hypothesis, which is in Python. But it's not about the framework either. So if you walk away from here and all you got is that, hey, there's a framework that looks interesting and I'm going to try it out, great. If you walk away and you think, ooh, that's going to change the way I start approaching how I solve problems, even better. A lot of my work and standing on stage these days is about me just sharing some of my work that I've done. Some of it is a little bit on the fringe and not mainstream. And I put it out here because I want people to try some things out and give feedback, and maybe there'll be a little spark that you could pick up and take forward. But let's just talk about thinking in properties. And I'm going to go right back to the beginning, which is, what is it that we do? 2 years ago, my mom turned 90. She lives 2,000 kilometers away from me, and I went to see her for her 90th birthday. And after 90 years, and my mom's a retired medical doctor who's never used a computer in her life, eventually caught me on the morning of her birthday and said, Aslam, I know I'm 90 years old today, but I still don't know what to tell my sisters what you do. And I said, you know, at the age of 90, you can just tell them what you told them every other day, which is, I work with computers. And it's such a horrible approximation. Last year, in October, I was asked to give a talk to a software development academy where young graduates, after 2 years of programming tuition, were graduating. And the hall was, the auditorium was filled with one half was students, the other half was parents. And so I tried to explain to the parents what we do. And I said, you must look over at your kids and just realize they do this magical thing where we take an idea and we transform it into something that we actually use on our computer, on our phone. The problem is that that magic starts with the problem and how we interact with that problem. And so I'm going to go back to right at the beginning. Okay? I'm competing with that. So above that sound of the background, we start off with the problem. And mostly this is the way I go about doing things. And I'm sorry if it's going to look linear and you come and you're going to say it's waterfall. It's not. You'll see why. There's conversations that we have. Some people write long documents and to describe the conversations, etc. I still enjoy the conversations because the nuance, etc. comes with that. And from that, we end up doing this thing called design in some way. We end up writing some code. And then we end up running that code. And it feels very linear, and that's what we do. But there's a lot of loops in between that. One of the loops is that we actually fix mistakes. Because we're not perfect right at the beginning, we end up fixing mistakes. And that happens more often than we like to think. But we do. But there's other interesting things that happen is that when we look at what's happening with the software that's used, we can make improvements. And the other thing that happens is that sometimes we learn something new about the problem, and we can do something better. So we can improve our design, etc. And sometimes we discover something new altogether. All because we started with a question and we're grappling with the question. And so I can give you another perspective, which is the first part is about focusing on understanding. And for that, that's dominated by the complexity of the domain, right? And so we're looking for tools to help us learn, help us understand more, and validate that understanding. If you go further, that part is about application of understanding. We've learned just a little bit, now we want to apply it. And we apply it in this weird thing called code. And we apply it in this weird thing that observes how people use our software. When we go through that fix and improvement phase, we're actually fine-tuning and updating our understanding. We're consistently doing that. We're fluctuating between analyzing and design and understanding all the time, right? And that side deals with the complexity of change. I like to think of us programming as how do we change going forward? Every line that we write is a change that moves us forward in some way. And so that is what I like to think about it. So we're looking for tools to help us move forward safely, deliberately. And so what tools do we have? When you look at that side, we've got continuous delivery, observability, reliability, and a whole bunch of other abilities that help us make software run. On the middle part, we've got practices that have been around for a long time, like test-driven development, refactoring. We've got patterns, we've got architectural styles, we've got different programming paradigms, we've got object-oriented programming and functional programming, all sorts of things, all designed to help us apply what we understand through conversation. Across all of that, what I strive for, which comes from domain-driven design, and it was significant for me, was trying to keep a consistent semantic language throughout that chain. But getting up to property-based testing, test-driven development helped me move forward safely. I had a love-hate relationship with it. I found it difficult to start with. I found it awkward to do. Test first, and why should I write it? And then I had to write stupid things like just put in a hard-coded value, and it helped me move forward. But after a while of just like doing reps in a gym, and I'm not good at gym work, you can see, I got better at it, and I found it actually made a difference for me. So it was something like this, and a really simple example is to sort a list. And all the katas and tutorials you see and videos you might watch on YouTube and workshops you go to, they'll say start off with something simple, like how do I sort an empty list, and what do I get? I'll get an empty list. And then we can do something like just put in one element in there and you get the same element back. And then you can test a list with unique elements. And then you can test a list with duplicate elements. And then you get adventurous and you say, let's stick in some floating point numbers instead. And so we go through this, and there's nothing wrong with this. It's not trivial. I'm using a trivial example so that you understand the flow and how we go about dealing with the problem. Incredibly powerful, incredibly effective. Why is it effective? I think it's effective because talking through concrete examples is a very effective way for us to collaborate. it's hard to talk in an abstract way with everybody. So we put an example up, and we talk to the example, and everyone can point at the example and say, yeah, I get that, and I get that. No, it's slightly different. That value should be like this. So collaborating with domain experts with concrete examples is incredibly effective, and I wouldn't want to take that away. It's really, really good. We also tend to get to the happy part quite quickly. We find the path which is either the simplest or the most common use case, and we get to that and we can understand it reasonably well. All because we're taking examples like how do we sort a list and move it through. It's a similar thing. But it can also be really difficult when the examples get more and more complex, when the domain, there's parts of the domain that has an increase in complexity. Most of the time, like insurance with marshmallow, pineapple, etc., it's a large domain with peaks of complexity, and it's the peaks of complexity that nail us. But in that peak of complexity, what happens is that we have to deal with it. The complexity normally comes from multiple variables that we're trying to juggle. And so reasoning with complex examples becomes difficult, and you probably recognize it in your own work. When you're sitting in a session and you're talking about things, and someone says, yeah, but it's not just about that. What about this? And you just put your head down and say, oh, no, not that thing again. We've all been there. Given the complexity, finding the small steps is really hard. Breaking something down into a small step that you could put into a test and run with it is really hard. And when you have giant tests, trying to chop them up is hard work. It's not trivial. So in some ways, it is kind of a little bit of magic that we do. And then you have to deal with test data. And then the more permutations there are with more variables, managing that test data is an absolute pain. It makes me hate doing this work because I've got this extra thing I've got to manage. And then people will say, take a snapshot of production and anonymize it. It's like, no, that's not what we should do. It's not precise enough. But this is why I think testing by example is the norm and why I've gotten away with it for so long. Yes, it has reduced the amount of defects and bugs, et cetera, and we've gotten better with our continuous integration and delivery pipelines. But mostly, we have to pay homage to incredibly tolerant users. Our users of our software, no matter how bad it is, how bad the experience, if there's a defect, they generally are forgiving because the moment you fix it, there's like all the love you get. That combination of having incredibly tolerant users and the economics of software means it becomes acceptable because we can actually drive and build software and amazing businesses with sometimes very mediocre software. We can, because users are tolerant. And I thank them all for that. If it wasn't for tolerant users, I wouldn't have gotten to 30 years of software development. Right, so that's what we do. We grapple with the ambiguity, we grapple with the unknown, we grapple with complexity, we grapple with lots of variables, etc. And here I want to talk about thinking with properties. So if you say thinking, what we're talking about is that we're talking about, well, Merriam-Webster says it's the activity of your mind to consider something, and a property is a quality belonging, to a particular individual or thing. So what we're after is the thing. So we want to apply our minds to find the unique traits of the thing. And the thing is the problem we're trying to solve, the software that we're trying to build. So let's try thinking about the properties of the thing. All right, so let's go back to sort. We can start by asking different questions. It's okay to start with examples, and it's a good starting point, but how about we ask different questions about the simple thing called sort? I can ask, what is always true when I sort a list? Take a moment and think. Yes, sir. There you go, same number of elements. Anyone else? Okay, let's try it out. Right, so one property is always true is that the sorted list, the length of it is the same as the one you gave it before it was sorted. Because if it wasn't, you lost elements or you added elements to it. Wrong. Can't be true. Well, that's actually the definition of it being sorted, right? The element here is less than the element that comes after it. So might as well, that always has to be true. Or equal to if there's duplicates. We want to ensure that the sorted list contains the same number of elements as the original list. Right? It must have the same count of all the elements. If there's 5 ones in the list, then in the output it must still have 5 ones. So notice what's happened here. It's so nuanced, it's so subtle. It messed me up because it says, what the hell are you asking me to do here? But I started looking at what we would call invariance, the truth about the act of sorting. And so now we want to write code for that. And notice here, it's nothing different. These are all assertions, just like any other testing language. It's Python, by the way. So that's an interesting starting point. And so let's put it inside of a method that can do the actual test for us, right? So this is a test method. It takes an unsorted list, it sorts it, and then it asserts all the properties, all the truths about the act of having sorted a list, comparing inputs to outputs. But we're not worried about values here, because notice I haven't specified any examples yet. Nothing. So where do the examples come from? Well, it's a function, so I can pass examples into that unsorted list parameter. And so I'm tempted to just write a little wrapper around this and just pass examples in, one by one as we've thought of them. Or I can use a framework that helps us with this, with property-based testing, which actually says, how about we generate 100 examples of lists of integers, and we shove that into that test method. So that is coming from this framework called Hypothesis, and it's a property-based testing framework for Python. They're all derived or inspired by QuickCheck, which comes from Haskell, and many other languages now have property-based testing frameworks. We just don't spend our time there. The one for Erlang, PropER is very good. The one for Scala Check is very good. I know JavaScript is very popular in the world today, but I can't speak about the quality of any of its property-based frameworks. And the good ones will have more or less the same things. And in this case here, a generator. And you can set an upper limit. OK. So now we have a way of generating test data to shove into here. And if you run it with PyTest, it's not that exciting. You get something boring like that that says 100% passed. But it did it 100 times. It ran 100 examples for us. The problem is that if I go and ask it to show me the examples it gave, I can, with this framework, ask it to show me all the input examples. I just took a snapshot of a few. And you can see it starts off with simple things like what we did as examples, an empty list, and then one item in the list, and then some weird things with negative numbers and big numbers. The question, though, is that what is the statistical distribution of those 100 sample lists? So we can get that as well, because it's important for us to understand the data of the domain. And if we're generating data based on some random seed, we better get an idea of what the heck is going on. So I can turn on the statistical output for Hypothesis. It gives us something that looks really nice. It tells us that, 86% of the lists have unique elements, 19% are empty with one element, 12% have duplicate elements, and it stopped because we said it was 100. Where did this classification come from? It didn't come from anywhere. I wrote a little bit of extra code that says, inspect the input unordered list and classify it for me. Right, so this is a really simple example, right, of sorting. But if you think about the domains that you work with, how often do you actually think about the frequency of use cases that happen in that domain? And how do you actually model how we handle those use cases? At the end of the day, everything about domain-driven design is about managing the data and make sure it doesn't lose its integrity no matter what we do to it, no matter which way we transform it. This has forced me to look at the properties of that domain to ensure I still have integrity and have a framework generate that data. One of the hardest things in property-based testing is writing the generators. And you can be quite sophisticated in that to get the distribution that you want. Right. Let's go back to that bit about testing floats. Nice idea. How would I now test? I have a little framework, a little bit of code that tests integers. And if I go in and I say, hey, let's do that with floats. Now I'm going to say, generate me 100 random lists of floats. That's all I did. Instead of integers, it's floats. And if I run this, it fails. We were happy the last time. It all passed. It failed. The interesting thing about this is that it tells me what the failure is. It tells me it tried a list with 0.0 and nan, and in Python, nan is not a number. It happens with floats. Sometimes you compute and you can't get the answer. And it can't sort nan. So we've got to do something about that to fix it. So having a property-based framework helps me do the right thing in terms of inspecting what happens in the domain. When I see something like this, I have to go back and have further conversations to ask, would we ever get a nan? Would it ever be a situation we have at this invalid value? Where should we handle it? Should we handle it in the function because it could happen? Or do we prevent it earlier on in somewhere else in the model? And so that starts helping us deal with that. And these kinds of failures that pop up when you're dealing with generating scenarios helps you actually have better conversations. It's a very precise question you can have. And that is the value of property-based testing. So, what did I learn? Having done this a few times, stumbled a lot, bloodied nose, etc. So I'm still not that comfortable with it, so I still do some example-based tests because it just gets me warmed up and going. But once I have a few of those, or one or two of those, I try to write it in a property style, like what you just saw. And so I do what I call building a property-based model, like you saw with that test that I had with all those assertions, all those properties, all those truths, etc. And then I do three things. I look at all the invariants, which tells me about correctness. We looked at invariants now. I look at the scenarios, which then asks me to think about what generators I'm going to use for that test. And generators is a whole bunch of thing all on its own. And then I also want to look at the data distribution. Bizarrely, if you're going to go further and explore this, you'll come across the word coverage in property-based testing. It's not lines of code coverage. This is coverage of data. What's the distribution of data? So I'm hesitant to use the word coverage. I'd rather have distribution. So if I do all of those and I stick them together like you just saw, then I run the model. And then I inspect the results. And two things pop out, generally. If it's a failure, I need to improve and question the truth that I thought was true. I made an assumption, I've got to fix it. I can fix the code sitting behind it, or I can do all of the above, right? The other part which is also interesting is that I can get pass, it can pass, but I don't get the coverage I wanted. I don't get the distribution I wanted. And so I've got to go back and update those generators and classifiers. And I run the model again, and then I inspect it, and I do it again. Until I have a model that represents the domain reasonably well. Now I've got something I can play with. I can have conversations about it. So, what it offered me, and what I looked back on, it encouraged me to ask the precise questions. I didn't just get fixated on the happy path. I looked at what didn't I understand by a failure or a poor statistical distribution of data, so I could go back to a domain expert and talk about it and narrow it down to what is reality. So TDD flow, red-green refactor, helps me move forward, make changes that move me forward in a very safe way. This PBT flow, I just made that up, by the way, so don't think that this is a real thing. It's not a thing, okay? So I just made it up based on the previous slides. So it's build, run, and inspect. That it forces me to go deeper into the domain, into the details, the minutiae of it. Right, let's try another example. The sort is interesting, but it's a computation. There's no state involved. Let's try something that has some state. Here's a simple counter. It starts off with 0. I can make it go up by 2. I can make it go down. I can reset it. I can make it go up. So I've got something that holds state, and it changes state. It transitions. So, from a property-based testing point of view, I'm going to use one of Hypothesis' base classes called rule-based state machine. What we're actually doing here, what we're going to do, is build up a simulation, a state machine simulation of that counter. And the first thing we're going to write is a rule for going up, right? And what this rule says is basically that when you go up, the difference between that you went up by was the amount that you said it should go up by. That was interesting. So that's it. Here's another rule for going down. And if you look here, the assertion here is slightly different, but it's basically the way I want to express it. I did it deliberately just to show that you can think of this in different ways, because we're interested in the thinking process here. Notice the generator at the top, I limited between 1 and 10. I did that just for an example in this talk, but just to show you the flexibility of how you can control your models when you're using property-based testing and what the frameworks offer you. It may be legitimate that you can only provide between 1 and 10 as the value that you can go up or down. Here's another rule. Right? This is an interesting one. It says that this rule called reset will only run under that condition, which is that if the counter value is greater than 0 is the only time you will run. What happens with property-based test runner is that as it's manipulating and calling up and down on the counter, it will try to call reset on the counter, but only if the counter is greater than 0. So you're getting really fine-grained control of what happens in the state machine and under what conditions certain transitions fire. And there's another invariant here, which is it's always greater than 0. The counter cannot go less than 0. So no matter which transition gets fired by the property-based test runner, it's always going to evaluate whether every condition in those rules and the invariants are held true. That's the truth about the domain for a simple thing like a counter. I run it, and it fails. The part in the middle is what's interesting. If you look at it, it says, I started off the state as the counter model, then I checked that invariant, then I decremented it with 1, and it failed. The invariant failed. So it's basically said, if you start off with 0 and you try to decrement it, something's wrong, it's broken. So it reveals to me a bug somewhere, a defect somewhere. It didn't go according to what I thought it was. The code, the model for counter did not go according to what it was. So if we go and look at the code, it's not trivial, it's contrived, I know. But, oops, we didn't check for less than 0. So we fix it, and we run it. But notice how much slower it is to run these stateful models. It's a lot slower. There's a lot more happening behind the scenes. I haven't even bothered trying to speed that up. This just has been really useful for me in modeling out these things. Right. Let's make a change to the code. Leave the model to one side. Let's put an upper limit to that counter. It can't go more than 20. It's a new requirement that's come in. Domain expert, some grand feature, we cannot have more than 20. Fine, let's do it. Make the code change. And run the same tests. This shows you the sequence of transitions that led to the failure. It says it started off with a new counter. It went up by 7. It went up by 6. It tried to go up by 8, exceeded 20, failed. We're not just getting the feedback that says that the test failed. We're getting essentially the sequence of events that led to the failure, because we modeled this as a state machine. For me, that was a really big deal. Ordinarily, I would have put a breakpoint in somewhere and started stepping through this to try to find that, or if we feel like it, we put print line statements everywhere and look at the output. This is a bit more sophisticated, a bit more precise. Update the invariant, run the test, and it passes. So that's a little bit of Python. You can try this in any other language, etc., and they're all pretty good, decent about this. But what else? What else about thinking in properties? I found it really hard. Implementing properties is not easy. It wasn't a natural way for me to think about it. I was annoyed with myself because I went back to Eric Evans' domain-driven design book, which I've referenced and looked at several times, and there's a section there on invariance and how we need to manage those things, etc., and how we model with that. But it doesn't come up often enough. It's not in our foreground. We do accidentally come across some rules and we put those in place, but we don't necessarily explicitly model them. And the way this has forced me to consider it. And so it felt awkward. But it is, in spite of that steep learning curve, and I found it a steep learning curve. In fact, I don't think it was a steeper learning curve than me trying to adopt TDD as a practice. I don't think so. So I'll cut myself some slack on that one. But it is a steep learning curve. And so if you're going to go there, be careful. Warnings that you might find it odd and awkward. Part of the steep learning curve, and I'm guilty of this as well, is that there aren't enough really, really good, chunky, meaty examples out there on the internet. You get what I did, which is sort and how do I prove addition is correct. Right? And so they sometimes are so simplistic that it's hard to think about what's the truth. Otherwise, you're starting to reach for axioms, and we're not interested in that right now. But I encourage you to try it with the domains that you are working with, because that's what I did. I'm guilty of not publishing anything around that. There's some other positive outcomes from this. One is that you get less code for more scenarios for free. You've got to look after that code like you look after your other tests, by example. But it genuinely feels more significant. It's like, this is a serious piece of code because it's modeling my thinking, my understanding. It does sometimes shake down bugs. You'll see a lot of claim from many advocates of property-based testing about amazing instances of how it found a bug that a human wouldn't have considered or whatever, like 17 particular database operations resulted in destroying the integrity of a table in a database, for example. But I've never gotten to that stage. Mostly it's caught my own mistakes. That's what it's done. And I'll take that as a win. I really do enjoy codifying the test data. It feels like I'm working deep in the domain when I'm codifying the test data. And having some code that represents the data felt a lot more manageable than having, files with data in it that we load up and read and transform and etc. So it felt a lot better than that. It felt better than some of the, fuzzy data generators that we use as well. This I cannot stress. It's no silver bullet. Absolutely none. I think, like every other thing that we do, it is something that it's worth being aware of, even if you don't practice it. Even if you don't reach out for property test framework, it's fine. If you start thinking about the invariance, etc., thinking about the distribution of data, you're already there. That's good. But don't take this and this talk and any other YouTube video you see about property-based testing and rush out and start throwing away all your other test suites because you've got property-based tests. It's not going to work like that. We need some of both. So it works, it's an and, it's not an or. It's really valuable, I think, for really complex domains. Like the counterexample is a trivial state transition that goes on, but most of the stuff that we work with is fairly complex. Going back to marshmallow insurance, coming up, that's modeling. That's an actuarial model, right? And so we've got to be precise about that. And I think this helps in those kinds of scenarios as well. The other thing I noticed is that I think less about happy paths and edge cases when I'm working in this way. And I'm actually accidentally just looking for a harmonized model over all the distributed, whatever the distribution of data is. And so I'm not doing anything beyond that. So the primitives of the domain contains the truth. And there's always an internal consistency to truth. And if the structure does not permit dialogue, then we must change the structure. If the model doesn't fit, let's start changing the model. But the truth lies in the domain and those conversations. This is the way I think about life: truth, structure, and dialogue, having a sense of struggle, sense of history, and a sense of humor. I'd like to end off by saying, what is it that we must do, that we absolutely have to do? I think we need to care more. We need to make a difference. And we need to make space for all of us. So, thank you for listening. 5 minutes earlier than planned. But really appreciate you taking the time out, because I know I stand between you and a drink. They call it a keynote, but it's a barrier to a networking event, so I'll pause there. Thank you very much, everyone.